begin the class with opening the floor for questions or comments or discussion on anything we've done so far. Anything at all? Okay. Maybe things will come up as we go along. So today I want to continue and finish up this idea of reversibility and apply it to a couple of equations of state, and then move on with discussing the first law. So again, on the Canvas website, there are some useful resources for the first law type of problems. I would like you all to take a look at those. And Wednesday, you can bring those up for our weekly discussion sessions with Abi, the TA for the course. I highly encourage you to make use of those resources. And of course, I'm available too. Okay, so let's move on. So last class, we were looking at reversible processes. And these were actually very important types of processes. Okay, so we had a reversible process, and we were discussing this in the context of work interactions, because those are actually easy to appreciate. And what we found is that if you have a work interaction, and this is a very general way to write work, we saw, which was minus P external times a differential in volume change. And so this is a differential amount of work. So this is a differential form. Whenever you see these D's, and soon we'll look at partial derivatives. So a partial derivative, if you may remember, is if you have a function of many variables. And so we saw with the ideal gas equation of state, P can be written as a function of temperature, volume, and N, right? And that was just nRT over V. So you see here that pressure is a function of many variables, right? I hope if there's any comments or if you don't understand why I'm saying this, please I really want you to just speak up, okay? There's nothing wrong with that. So pressure is a function of temperature, volume, and N. And so if you have a function of many variables and you want to take a look at how that function changes with any change in another variable that it depends on, right? It's sort of like a rate, right? So what's the rate of change of pressure with respect to temperature, for instance? It's a rate. That's what a derivative is. It's essentially a rate. Rate of change it's the change of something with how something else changes. So if we wanted to know how pressure changes with respect to temperature, and if we held everything else constant, so that means volume and N, this partial derivative, this idea of a partial derivative, and it's kind of obvious, right? Because it's partial because you're holding some of the variables constant. We would write this as the partial of the pressure. So instead of a D, we would use this Greek lowercase delta and we have to carry along the dependence of pressure on all of the variables on which it depends. So we have temperature, volume, and N. But in this case, we're interested in how pressure changes with temperature. So on the bottom, instead of that D, we would have this squiggly little thing. It's a Greek symbol, okay? And what we would do is signify that volume and N are constant. And this is how we do it. Okay? And this is what a partial derivative is. We only want to focus on how a function changes with one of the variables on which it depends, while we hold all the other variables constant. Okay? And so this is what we mean by a partial derivative of pressure with respect to temperature, holding volume and number of moles constant. Okay, so this is a partial derivative. I won't write all of the words out, but you can always go back to this video later. Okay, and for the ideal gas equation of state, which is the simplest, and so we use it as an example in almost all cases, it's easy to manipulate. We know what the partial of pressure with respect to temperature at constant volume is. All we have to do is treat this equation, okay, because we've stipulated that these guys are constant. The only thing that varies in this equation is T, and everything else is a constant, because that's the way we set it, right? So this partial then, temperature, volume, and N with respect to T, if we hold volume and n constant is just going to be n r over v, because we just take the derivative with respect to t, and since t is there linearly, there's no exponent on the t, there's no log of t, there's no e raised to the t, it's just the t. It's a very simple derivative. And what we find is that the partial of pressure with respect to temperature holding constant n and v is equal to nr over v. And it makes sense, n and v appear in the result because they were constants. So everything checks out. It all makes sense, okay? We can go a little bit further. I'm doing a digression here, but I guess it's important because we're using a simple equation of state here. Everyone follow me so far? Have I lost anyone? It's all pretty clear, right? We can do the same with respect to volume, okay? So the pressure derivative, partial pressure and you know that this is a function of TVN. Now we're gonna let volume be the thing that changes, but what we're gonna hold constant is temperature and then. Okay, that's how we signify that. So this is just a notation, the partial of P, which is in the numerator of this guy, with respect to volume, here holding temperature and n constant is going to be, well now we have volume in the denominator. Okay, if we look here, we see that volume is in the denominator. So this actually is minus nRT over v squared. That's the derivative when you take something that has 1 over v or 1 over x. Okay, so if you don't remember, this is just a refresher in calculus. This is something you can go and refresh yourselves. But the new thing here is this notation and perhaps the concept of a partial derivative. But taking the derivative of 1 over x should be something that you can go back and review. This is from freshman calculus. Okay, any questions? So we know now that, so I'm going to go back to our idea of reversibility. This was a bit of a digression, but we'll use this concept. Okay, it's very important. So if you think about that as you refresh as you go over your notes. So we saw that for dW, for work, this is the most general form. And if we have a process that's reversible, okay, the system pressure can be represented by an equation of state all along the process. Okay. So that means that there is no difference between external pressure, P external, and P that is given by temperature, volume, and N. Okay. So this is the external pressure, and this is the pressure given by equation of state. Any questions? Any questions at all? So what happens then for a reversible process? So in the case of a reversible process, dW, reversible, is equal to minus pressure of temperature, volume, and perhaps there are other variables, times dV. Okay? So this is very important. So let me remind everyone, and here, this is in your notes, again, to prevent confusion later, this is something that you have to develop a methodology for how you can, alert yourself for something that's very important. So for a reversible process, okay, we have this, there's no P external, but the reversible process is a subset of all general processes. So again, dW is always minus P external dV, okay? This is always, okay? Because that's the most general, okay? A reversible process is a subset now of a general case. Okay? We made some stipulations on what this reversible process is. It's a process where ideally, it's an idealized process where you carry out this process in a manner that's so slow, for instance, that the system always remains in equilibrium. Okay? Any questions? or comments? Okay. All right. So last class then, we found that for an expansion, so let's consider the implications of reversibility, or the consequences, implications or consequences of reversibility. Okay, so the example we used last class was compression. Compression of a gas. Okay, and what we said was, all right, here's our gas, here's this piston assembly. Okay, we start with some pressure, external, we compress it. Okay. So here we have T1 and V1, and here we have T2 and V2, where V2 is less than V1. Okay, so here the surroundings do work. Surroundings do work on system, which is our gas. So let me write that down. Gas is equal to the system. So I know what I'm talking about. So the surroundings do work on the system. That means whether we have reversible or irreversible work, work is always a positive. Work is always positive. Okay, whether it's reversible or irreversible, right? Work is always going to be positive because work was done on the system to compress it. And what we found, that work reversible, does anyone remember? Compared to work irreversible, in terms of their values, if we were to assign numbers to these guys, does anyone remember if there would be an equal sign in between?
Work irreversible was always bigger than work reversible.
Ah, good, exactly. That's right. So the work reversible, and if we were to write this in differential form, can you state that in differential form? How would this look in differential form? So if you wanted to look at differential amount, differential W's.
dW rev equals dW irreversible minus delta.
Okay, but just use the same format. So if we were to use if we were to compare dW rev versus dW irrev, it would be, what would I write here after what would I write here next?
Oh, greater than?
Why greater?
Do less than, because they're differentials of the same function.
Yeah, right. It's just that you put a D there. Does everyone see what the differentials would have to be the same? If you carry out a process in segments, all of those segments, since they're each reversible, so if I were to carry out on a pressure volume diagram from state 1 to state 2, let's say, and I have a reversible process, right? This statement is for the whole process. This statement is for any small piece of that process. But since the whole process is since the whole process, if we were to compare reversible versus irreversible, dW reversible would always have to be less than dW irreversible. Okay? It would always have to be that way. Did I confuse people, or is that still an issue? Because if I'm comparing just small pieces of reversible versus irreversible, the same two irreversible and reversible processes, their differential amounts would have to obey the same inequality as the total amount. Okay? So these two equations or inequalities are the same, they're equivalent. Okay, so what this means is for the compression, if you do the compression reversibly, you have to do less work, the surroundings have to do less work on the system, than if the compression was done irreversibly. So let me repeat that. So this is very important for the case of this reversible process. And it's given right here, that if you do this compression, which is work being done on a system, right? So now let's say you're the external environment, you're going to have to do work. So if you can do the process reversibly, you will have to do less work as the surroundings than you would if you did the process irreversibly. And that's what is embodied in this inequality. And this is the importance of what a reversible process means in the context of work. Okay, so when surroundings do work on a system, okay, if that interaction is through a reversible process, the surroundings have to do the least amount of work. And that's good. If you have to do work on something, you want to do the least amount. So this is why reversible processes are so important. Now you may ask, well, okay, in the idealized case, the reversible process is infinitely slow. And so wait a second, if you're like doing something slowly for an infinite amount of time, wouldn't that kind of seem to suggest that you're doing an infinite amount of work? But of course, that's now, you're making this a rate. So the amount of work you're doing, let's say by pushing on that tire pump or pulling off that tape, if you do it really, really slowly, you can feel it, right? Just try pumping a bicycle tire. If you do it really, really fast, which would be irreversible, you can just feel the force. But if actually you do it slowly, you can feel yourself, it's palpable that you're doing less work. It's much easier to push it down slowly, 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 rather than to take a deep breath and just kind of slam the thing down. Okay, so in the end, the reversible process allows you to do less work on a system than the irreversible process. Okay, is that clear? And this is a general thing. So if the surroundings do work on a system, in a reversible process, the work will always be less than that in an irreversible process, okay? And now the important thing is, let's reverse it. Let's say now that we have expansion. So this was for compression of a gas, okay? And the compression means that the external surroundings do work on a system. Let's say we have expansion of a gas. Okay. And in an expansion of the gas, again, the system is our gas. The system is going to do work on the surroundings. So in this case, what we have is we have our gas at T1 and V1. And we have some P external. We always have to write that P external, but now it's going to expand. Okay. Gas does work. Gas, which is our system, does work. And what happens is that there's an expansion against this external pressure, T2 and V2. Okay, where now V2 is greater than V1 because we have expansion. So the system is doing work. System does work on the surroundings. Now, if the system were an engine, for instance, an engine in your car, okay, or some sort of a motor or an engine in a power generating plant or something like that, you would want to get the most. You would want to get the most out of the system, right? You would want to get the most work out of the system. Okay. So remember, when the system does work, what is the sign? This is very important of that work.
Negative.
Sorry?
Negative.
Yes, negative. Very good. And I hope, so as a check along, you know, your understanding of this course material, I hope that everyone could answer that response with negative, because that is the correct answer. The work, when the system does work, is negative. And so at this point in the course, I really want, as a sort of feedback for you as a check on where you should be, That should be obvious now. Okay, that's so fundamental to the course that you need to be on top of that concept. So the sign of that work is negative, exactly, because that was our sign convention. Negative work means that the system has done work on the surroundings. So work is negative. So the total work is less than 0 because the system did work. It turns out that we can use the same inequality right here that we used above for the case of expansion or the case when the system does work. So let's write those inequalities again. W reversible is less than W irreversible, or dW reversible is less than dW. And this is, so this, the inequalities I wrote in red are the same as the inequalities here in this box. They're the same, nothing has changed. And that's great because you don't have to worry about anything, whether you have expansion, compression, or the system doing work on the surroundings or the surroundings doing work on the systems, the same inequalities hold. And they should, they have to. You can't have any difference. This is symmetry, okay? You might have heard physicists talk about symmetry, very fancy idea, but this is symmetry. And this is so important, and in my opinion, so cool. Because now, since work is negative, when the system does work, work is negative, you want that work to be the most negative it can be. Why? Because you're getting work out of the system, and because of our sign convention, SIGN, when the system does work on the surroundings, you want that work to have a sign that's negative. You want it to be negative. You want it to be less than 0. And you want it to be a very large negative number because you want to get the most work out of that system, right? If you're going to invest in some process in a plant or in a car or whatever, and you're looking to get work out, you want to get the most bang for your buck. So what that means is that you want W to be as negative as possible. What we see here then, if we apply our inequalities that compare the work from reversible and irreversible processes, we see that the work that comes from a reversible process is less than the work that you get from an irreversible process. Okay, it's the same inequalities that we had up here. Okay, work reversible less than work irreversible, and of course the same applies for the differential amounts. Work reversible is less than work irreversible. But in the case when the system does work, this is awesome because work irreversible is going to be less than the work irreversible, and it's going to be negative. So if the system does work, let's say, and I'll put some numbers here. The work reversible may be minus 100 joules. Okay. Work irreversible may be minus 50 joules. So you see here that in this case, you got twice as much work, 2 times more work from the system than in second case. Does everyone see that? Because we chose our convention that work is negative when the system is doing work, you want the work to be negative, which it is in both cases, but the reversible work is much more negative, twice as much than the work irreversible. And so in a reversible expansion where the system does work on the surroundings, you get a lot more work out from the system. You essentially exploit the system twice as much, and that's a good thing if you want to get work out. Okay, so I've said it in many different ways. Is that clear? And this again highlights this idea of a reversible process and why it's so important. Okay, so I'll just pause a few seconds here for any comments, feedback, questions.
So if you have a reversible process and it compresses and then it reversibly expands again, would the work be equal to 0 or no? Or does it depend?
Oh, great question. Great question. All right. Great question. Whoa, that's a very good question. In that case, your overall work, if you had reversible expansion and compression, would be 0. That's that one case. And let's take a look at this. Awesome question. So what we're gonna do is we're going to use a pressure volume diagram. Okay, and we're going to use our ideal gas equation of state again, because it's so basic and simple for us, we can always use it. PV is equal to nRT, and we're going to consider an isothermal process. I'm going to answer your question in a long-winded manner, because it's very important. So we can write pressure as a function of temperature, volume, and N is equal to nRT over V. Okay, I'm gonna move fast with these manipulations. I think everyone can follow this basic algebra. So we see here that P is a function of 1 over V. This is a 1 over X type of a function when we hold temperature constant. Okay, and we're going to always have N constant. Okay, so this is isothermal. That means iso equal thermal T, isothermal constant temperature. So this is a 1 over X type of function. And so on a plot of pressure volume, it would sort of look like 1 over X. It's 1 over V because our X is volume. It would kind of look like this. Okay, and so here are the two endpoints. So now this is the ideal gas equation of state, our man-made model, right? Because we know that it was just something that was experimentally observed, and we sort of fit a function to it to say, oh, okay, PV equals nRT kind of fits all our data. So it was man-made. But if we hold temperature constant, pressure and volume are related in this manner, okay? And so the two dots represent two equilibrium states at initial and final, and all the states along this curve, all the points that are intermediate along this curve are equilibrium states, and they all correspond or they all adhere to this model, okay? At any point along this process, this equation has to be met, and it will, at constant temperature. Okay, so that's what we've plotted here. So as the question was, if we start here, okay, if we start here and we go to here, so these are our two equilibrium states. One comes before two, so we start at 1 and we go to 2, okay? The reversible work, does anyone sort of want to offer what they would think the reversible work here would be in terms of what they know about integrals? So we know now that dW, the differential, would be minus P of temperature, volume, and dV. We know that because we don't have to worry about P external. Now we use this guy because it's reversible. Does anyone want to take a guess as what that area, oops, I erased it. What the work was?
The integral under the curve, but it'd be ln of V1 or over V2.
Oh, okay, you're already going, okay. Okay, can I come back to that? You're right. Let me just come back to that, okay? Graphically, since we're going this direction, okay, the work would be I just want to make this visual. Sometimes it's easier to see a picture. So this is the work if you were to go reversibly from equilibrium state 1 to equilibrium state 2. Remember, the integral is an area under a curve. And yes, we will do this integral in a moment. I'm going to do that as examples. Just you're ahead of me. But for the reversible compression, we see that the area under the curve, which is work, is given by these slanted red lines. So that would be the work that's required for the compression if you do it reversibly. Is that okay? Everyone okay with that? And you see here that it's actually a very unique number. It's a very unique number in that there's only one work reversible. There's only one way to go from 1 to 2 at constant temperature reversibly if your fluid, if your gas obeys the ideal gas equation of state. Now, if you were to let the gas expand reversibly, if you were to allow the gas to expand, meaning that now you're going to go from equilibrium state 2 to 1, which we can say, all right, it's going to be blue. It's going to go in this direction, okay? What's going to be the area under the curve? Well, the area under the curve is still the same as what I've shown by the red slanted lines, correct? The only difference now is that that area is going to be assigned a negative sign, SIGN, because we know that when the system does work, whatever that work is, it has to be negative. So in fact, what happens then is for the reverse process, the expansion, which is also reversible, you get area that's this, it's the same area. It's the same area under the curve, but it's negative. And so if we go reversibly from 1 to 2, and then reversibly back from 2 to 1, it's exactly correct that there is no work done in that cycle. And so this is a very special case where that cycle allows for zero work. Okay, is everyone clear on that? That was a good question, and it's easy to see visually. I hear silence, so I'm assuming there's no, it was clear.
It was clear.
For irreversible work, I guess this diagram wouldn't be true.
Exactly. You want to, okay, so let's compare the reversible and irreversible. You want to see it in diagram form? It's in your reading, but I can discuss it. What do you want to look at, compression or expansion?
Expansion.
Expansion, okay. You would have to pick the complicated one because that's negative, but okay, that's fine. Okay, so if we have expansion, this will be our initial state 1, and this will be our final state 2, and we're going to be going in this direction, okay? And again, let me just note, this is isothermal, ideal gas equation of state, and we're going to do the same thing here, isothermal, ideal gas equation of state. So what I've plotted on this curve is the ideal gas equation of state plotted with T as a constant. And again, remember that P then is just, it goes as 1 over V. And instead of writing all the constants, I just indicate that it goes as with this squiggly little thing 1 over V. And that's why you get this qualitative curve that looks like this. It's a 1 over X function. So this is the ideal gas equation of state model that I've shown as a curve. Now, and this is reversible. So if you were to go from 1 to 2 in a reversible process under isothermal conditions, this is what that process would look like on this plot of pressure versus volume. Okay, again, mouthful here, but this is a very important condition that it's isothermal. We have ideal gas equation of state, and it's reversible. Okay, so all of these three things go into representing this process through this black curve that you see on the graph so far. So this is the reversible expansion. Okay, now if you were to do this irreversibly, okay, we could do it in many, many different ways. We could do it in many, many different ways. Okay, I'm not going to show you all the different ways because there's too many, but I'm going to show you just one path to emphasize the point. So before I do that, is everyone clear that for this reversible process, okay, the work is given by the negative of the area. So it's this area here. Again, I'm going to go outside of the lines of the graph, but you know, just that's that area. Okay, it's this area that I've shown. That's the work. Just take the negative of that and you get the expansion work that the system does. Is everyone okay with that? Okay, now, if you want to do this irreversibly, let's look at the irreversible process. So this reversible process, again, ideal, it's ideal. If you wanted to do this, the system, let's say you had your piston assembly. Whoa, what did I just do? I don't want that. Okay. Let's do that. So here's your piston assembly. And what this means is if you have a gas, you have a whole bunch of little weights on this piston head. Let's say they're like infinitesimal little weights, like grains of sand. Okay, and I'm sort of not, you know, you have a mound of sand with infinitesimal little grains on it. Okay, that's what I've shown here. Each one of these little grains has an infinitesimal amount of mass. And so this reversible process here, okay, corresponds to plucking each grain off of the cylinder head. This is an analogy again, right? The reversible process is an idealization. So we have to use analogies to sort of think about it. So for this case here, we're going to pick one of these grains of sand. They're so light that it's imperceptible, right, when this piston head moves up, when you remove that little grain of sand. But that piston head is going to gradually over time, as you pick more and more and more of these grains of sand, you'll see over time that, oh, it's going to rise. And the gas essentially is doing work on the surroundings by pushing up on this piston head. Okay? All right. If we were to do this irreversibly, so this corresponds to a reversible case. Pluck individual grains of sand over infinite time. Okay, so this is the reversible case. That corresponds to this guy here. Now what we could do if you wanted to do it irreversibly, and so does everyone appreciate now that when I pick these individual grains of sand off of this piston head, think about being a molecule. So imagine yourself a molecule in this gas or a particle of gas, right? The thing is moving above you so imperceptibly slowly that you're always in equilibrium. You can't grasp that subtle difference between one grain of sand. It's like so light that you're like, all right, it's equilibrium, everything is cool, right? Pretty good. I'm gonna take my time and do the work on the surroundings. Okay, so that's what, from the perspective of a molecule, this reversibility means. You know, the molecule is like, all right, everything is cool. No need for turbulence, no need for chaos, no need for, whatever. I'm pretty chill. Now let's do this irreversibly. And for the irreversible analogy, okay, what I'm going to say is that I have the same amount of sand, okay, as I did for the reversible case, but what I'm going to do is I'm going to just put it in two lumps. So on this side, I'm going to have the same amount of sand, but in a lump here. Not 1/2. Let's split that total amount of sand into two lumps. So a red lump, okay, and a blue lump. And we'll put the blue lump here. Okay, and so the blue plus red is equal to black. And by that, what I mean is that the lump of red sand on the right plus the lump of blue sand on the right is equal to all of that lump of black sand on the left. Okay? So, if you're going to do this irreversibly, okay, what I'm going to do is I'm going to come to this piston assembly, okay, and I'm just going to take all at once. I'm going to take that red lump of sand, all of those grains of sand in that red lump. I'm just going to like remove it. So essentially what I have left is 1/2 of what I had initially, okay, because I split the total amount of sand into a red and blue lump. So I'm just going to come along and I say, whatever, I'm going to take this red lump and remove it, okay? And that red lump, it's going to be sizable amount. It's not going to be like, obviously it's not going to be the same like 1 grain of sand, right? I removed a whole bunch of sand there. So it's going to be pretty shocking to the system. And so if you're a molecule in this gas, right, all of a sudden you're going to be like, oh, the piston head has moved, because you removed, the external environment has now moved the sand away from the piston head. And now you're like this molecule, the moment, oops, the moment that that sand has been removed, here's still the blue lumps. Okay, you still have the blue lumps. Whoops, it should be black. So you still have the blue lumps. But now what happens, the instant you remove that red lump, the instant, what you're going to have is all your gas molecules, I'm going to let them be green. So here are the gas molecules. Okay, these are the gas molecules. And at the instant you remove that red lump, this thing, the piston head is going to shift. It's going to be a violent shift, right? It's just going to move. The thing, it doesn't want to be there. The gas is going to experience this region of whatever. It doesn't know what's there, right? And so all of these molecules now are going to like, there's going to be some sort of turbulence because they're constantly moving. There's kinetic energy of the molecules. And now they see that, oh, wait a second, there's all this space, you know, what's going on? You have no equilibrium at this point. Okay? And so for that moment, there's going to be irreversibilities that exist in the system. You're going to have all sorts of chaotic dynamics in the system, turbulence. You might have eddies. The gas might be swirling around. It might be so brief, but it will be there at the molecular level. Okay, you can't see it, but it's there, and it's very quick. Okay, so the system is not in equilibrium anymore for that moment of time, but it quickly comes to fill that void and equilibrate. Okay, the next thing we can do after this is remove the blue lump. Okay, so we have two stages. So if you go back to our process here, where we have this expansion, what we're doing is that we start here, okay? But if we're doing this irreversibly, we're going to remove the red lump. And by removing the red lump, what have we done to the pressure on the system? By removing that red lump.
Decreased it.
Decreased it, exactly. And have we done it gradually, or have we done it quite violently?
Violently, rapidly.
Violently. And by violently, what I mean is that it's a step change. We did it instantaneously. So in fact, what happens is that instantaneously, by removing that red lump, we change the system pressure from what it was at P1, where the system was equilibrium, okay, at 0.1, to something that where now the system is no longer at equilibrium. It's at this kind of a condition here that at that instant where we remove that lump, the instant, right? You have to keep that in mind, the instant, right? And that's why I say it's violent, because you do it just like you're pumping up a tire, right? You're really, you know, some people do it that way and some people do it slowly, right? So the moment you remove that pressure, the system pressure is going to fall, right? And we're not going to worry about what happens during that non-equilibrium period, okay? There's a whole branch of thermo that deals with non-equilibrium stuff. But we won't deal with that. So what happens is that the pressure now falls to this guy, this value, whatever that pressure is, right? We can say P intermediate 1. And now the volume expands to fill that pressure. So once we remove that red lump of sand, that piston is going to stop at a certain volume, okay, because we had that pressure. And so now the gas will fill that volume, okay? So again, we remove the red lump, okay? The piston head moves up because there's less pressure, and the gas is going to now equilibrate at that next volume, whatever that volume may be. In this case, it's going to correspond to the pressure. This is again at isothermal conditions. So now the volume is going to change to this guy because we reduced the pressure. Okay, we reduced the pressure by removing the lump of sand, that red lump, and we let the system equilibrate. Okay, and what happens is that the system now equilibrates at this point where we have this P int 1, the intermediate pressure 1, and some volume right here, which is V intermediate 1. Okay. So we remove the red lump, the pressure goes down to P intermediate 1. Okay. Instantaneously, it goes down instantaneously. and then the volume expands, and then the volume expands to V intermediate 1. Okay, and so the work that was done in that stage, if you want to visualize it pictorially, is this. That's the work. It's just the pressure times the volume. Okay, that's the area under the curve. Finally, what we do is we remove the blue lump, right? We still have this blue lump here. We're going to remove that blue lump, okay? And that's going to take the system now to a pressure that corresponds to this guy. Again, oops, sorry, we're not going to go there. That pressure, since we're here now, is going to correspond to this guy once we remove the blue lump. So again, after the system has equilibrated at V intermediate 1 and P intermediate 1, we're going to reduce the pressure by removing the blue lump. Again, it's going to be violent. We're going to remove that blue lump. Okay. The system is going to be in non-equilibrium, and what it's going to do is going to equilibrate to the final volume, because we know that the two amounts of sand, whether we did it reversibly or irreversibly, are the same. And so now the work is going to correspond to that. Okay. So for the irreversible case, we'll use the two lumps of sand. The work that we get out from this expansion is the combination of the red areas and the blue areas. Okay. And what we notice is that when we do the process irreversibly in these two stages, we get less work because the area that's under the red box and the blue box, or the red lines and the blue lines, is less than the area that we had with that black curve. So we see here that there's a bit of areas, namely this part and this part, that we lost in terms of work. So we lost that amount of work by doing it irreversibly. Had we done it reversibly, we would have obtained that extra work that's given in these regions right here. Did everyone see that? So we lost out on that work. And so this is a long-winded answer to your question about what this looks like. Okay, does that make sense?
Yeah, thank you.
Okay, so
Yeah.
Okay, it looks like I always talk too much. What I was going to do was compute the reversible work for the ideal gas, but I guess I'll do that next class. And I also wanted to use the van der Waals equation of state, which is a little bit more realistic equation of state. It's the next level above the ideal gas. So I guess what I'll do is I'll do that next class, and then we're going to look at we're going to start doing partial derivatives and working with partial derivatives of functions of U, the internal energy, or the energy, and look at the first law and some of the things that arise from the first law. Okay, I guess I will stop there for today and leave the final moments for any questions. I guess I have an office hour starting at 11:10, so I'll be here. But if there's any other questions for the moment, I'm happy to entertain them. It was a very good discussion, very good questions, this class. Okay, I wish you all a good week then, and if I'll be around. Okay, thanks for your attention and participation.
Thank you.
Okay.
Thank you.
Thank you.
Take care. Yep.
Good
Bye-bye.
day.